A skyscraper 4 football fields long, ripped from its foundation and dumped into the Pacific. That is a modern, ultra-large container ship. From the dock, these iron fortresses look invincible, but the reality is far more complex. If these ships were built to be perfectly rigid, they would face significant structural challenges within weeks. To survive the ocean, engineers designed vessels that allow for a degree of controlled flexibility. When these Titan ships hit a massive swell, the hull is designed to ripple, bend, and twist. This is not a design flaw, it is a requirement for survival. If the hull stayed entirely stiff, the immense pressure of the surging water could potentially compromise the ship's structural integrity. You are watching a 400-meter-long tightrope walk happening in slow motion every single hour. Yet with thousands of tons of cargo stacked 10 stories high and nothing but steel cables anchoring them against the abyss, even this mechanical dance has a breaking point. To understand that tension, look at the ship not as a static object but as a massive floating stability machine. When you load a vessel to the scale of the CMA CGM Jacques Saade, which features a gross tonnage of 336,587, you are balancing a small city on a flexible frame. If a crane operator places too much steel in one section of the hold, the ship doesn't just lean to one side. It undergoes a process called hogging or sagging, where the mass of the cargo causes the central hull to bow or dip. If you fail to calculate the weight of every individual box against the buoyancy of the hull, the ship faces significant structural strain. It is a constant, invisible calculation that determines whether the vessel survives the waves or faces severe damage, as the cargo geometry itself creates the next threat. Once you move past the mathematical danger of the hull, you're faced with a logistical challenge inside the cargo belly. If these thousands of containers were just stacked like haphazard building blocks, the first significant ocean swell would turn the hold into a chaotic, shifting avalanche of metal. To prevent this, the interior of a massive container vessel is a masterpiece of rigid geometry. Engineers build the cargo holds with vertical steel cell guides that run the depth of the ship. These steel tracks act as an internal skeleton. When a crane lowers a shipping container into the bay, it slides into these vertical slots until the corner castings of the box lock into the guides. It creates a physical metal-on-metal connection that prevents lateral movement. Even when the ship is hammered by massive waves or tilting at severe angles, these boxes are physically locked into the frame of the vessel. The cargo acts less like a collection of individual units and more like a singular, solid mass of steel that is integrated into the ship's own structural design. That physical integration is a primary barrier, keeping these thousands of units from shifting during the voyage. But how do you keep that massive tower of steel from tipping over when it hits a rogue wave? If these ships relied solely on their steel frames, they would be far too top-heavy to survive the journey. The secret lies in a hidden system of ballast tanks that run the length of the hull. Think of these tanks as a liquid counterweight that the crew can manipulate. When the ship is fully loaded with cargo, these tanks are adjusted to keep the vessel riding at the proper trim and draft. However, as the ship burns through its fuel or drops off containers at different ports, the center of gravity begins to shift. If the crew failed to manage this, the ship could become unstable, leading to a dangerous roll in heavy weather. By pumping water in or out of these specific segmented tanks, the crew can actively lower the center of gravity to keep everything balanced. It is a constant game of mathematical trade-offs to ensure the ship maintains its trim and doesn't lean dangerously to one side. Yet even with the ballast system perfectly balanced, the highest stacks on deck are now facing the open wind. Once those heavy containers rise above the ship's protective steel sidewalls, the security of the cargo changes. Deep inside the hold, you have the benefit of those vertical steel cell guides that physically lock the containers into place. It is a rigid, reliable system. But on the open deck, those steel guides disappear. The massive towers of metal are suddenly fighting the wind, the swells of the ocean, and the violent motion of the ship with hardware to hold them steady. That is where the lashing process begins to keep a stack of containers from toppling into the sea. Crews rely on a combination of twist locks and heavy steel lashing rods. You have to imagine these towering multi-story stacks of steel moving in unison with the hull, absorbing the energy of a rolling wave. If just one of those individual locks fails, the entire column can lose its structural integrity. It is an intense mechanical struggle against gravity and momentum. While the ballast tanks manage the ship's balance from below, these lashed connections are a critical defense between a perfectly organized deck and a potential catastrophe during a storm. The intensity of that struggle depends heavily on the engine's raw power. Keeping those thousands of containers balanced is only half the battle. Once you realize just how precarious that structure is, you have to wonder how something so massive even moves through the water without tearing itself apart. The answer lies deep inside the belly of the ship, where a singular machine dominates the entire interior space. We are talking about the WinGD-11X92B main engine. This is an absolute titan of engineering that is rated at 58,600 kilowatts or 79,500 horsepower. To put that into perspective, it is enough raw energy to power a small city, yet it is all channeled into driving a single colossal propeller through the crushing resistance of the open ocean. This sheer force supports the vessel's operation. During a violent storm, if a ship loses its forward momentum, it becomes a sitting duck at the mercy of chaotic swells. That engine must work constantly to drive the vessel through the water, effectively using that forward push to fight back against the massive forces trying to twist the hull. The engine is the heartbeat that maintains the ship's orientation. Without that immense, consistent output, all those intricate ballast systems and lashing rods would face increased strain under the weight of the seas, especially when dealing with the ship's volatile fuel. Maintaining that forward momentum requires more than just raw horsepower. It demands a fuel source that can keep up with a vessel at this scale. This has pushed naval architects into the world of cryogenic engineering. Take the CMA CGM Jacques Saade, built in 2020. This ship features a 660,000 cubic foot LNG fuel tank maintained at -258 degrees Fahrenheit. Think about the sheer audacity of that. You're hauling a freezing, volatile lake of liquefied natural gas inside the belly of a 400-meter ship that is already bending under the pressure of the ocean. The temperature difference between that tank and the surrounding seawater creates a permanent internal thermal stress that engineers account for in the hull design. If the insulation systems fail or the tank breaches, you're not just looking at a fuel leak, you're dealing with a shift in the center of gravity and the structural integrity of the ship. It turns the vessel into a massive floating thermos. Designing a ship to be a cold storage facility while simultaneously allowing it to flex with the waves is a balancing act of extreme thermal physics. Yet, even with these cryogenic risks, these vessels are designed to withstand significant ocean forces. It feels like a statistical impossibility when you consider the sheer scale of the 400-meter Maersk Triple-E class vessel, which reaches 59 meters in width and 73 meters in height. But the secret is the stacking of distinct safety layers that transform a hydrostatic challenge into a consistent logistical miracle. Inside the cavernous hold, steel cell guides lock the heavy cargo into rigid vertical columns, while the ballast system constantly shifts liquid weight through tanks to counter the ocean's unpredictable, violent motion. Above the waterline, your lashing rods and twist locks hold the deck in a tight mechanical grip. Every single component acts as a redundancy for the last, because the ship is designed to be slightly flexible. These systems work in tandem to distribute the physical stresses across the entire length of the hull rather than concentrating them on a single, fragile point. By integrating the cargo as part of the vessel's internal skeleton and managing the center of gravity with precision, the ship maintains a fragile but functional equilibrium on the open water. This goes beyond just how these giants survive the waves. It is about understanding the massive, invisible nervous system that carries the lifeblood of the global economy on its back. When you look at these 400-meter steel behemoths, you aren't just seeing a hull in a container. You're looking at one of the most complex, high-stakes balancing acts ever designed by human hands. Every time one of these vessels leaves port, it is defying the odds of physics to ensure the shelves in your local store stay stocked. We have barely scratched the surface of how the maritime industry keeps this industrial backbone from failing under its own weight. If you found this dive into the engineering of the impossible as fascinating as I did, you should tag along for more. Every week, we pull back the curtain on the massive, often chaotic infrastructure that most people ignore until it suddenly stops working. I'm putting together a deep dive into the hidden logistics chains that dictate what you buy and where it comes from. Subscribe to keep up with the series and ensure you never look at a cargo ship the same way again.